Quiet. Close the door.
Open it up.
What?
Hey everyone, let's get started. So hi, my name is Kaival. I'm a software engineer at Amazon on the product search team. So our team owns the Lucene-based search engine for Amazon shopping app and website. And I'm super interested in Lucene and vector search in general. So today I'm going to be speaking about the Faiss integration in Lucene. So super grateful to be here, and I'm also very nervous. So please let me know if I'm rushing through things or if something is unclear. So yeah, let's get started. So what is Faiss? So Faiss is short for Facebook AI Similarity Search. Faiss is a library for efficient similarity search and clustering of dense vectors. So it is developed and maintained by Meta, and an important reason you can even look at its code and add it to Lucene is it comes with the MIT license, and it's written in C++. But what are vectors and why should we care about them? So a vector is simply a point in an n-dimensional space. A vector has both magnitude and direction. So a vector is represented as a series of float values where each of these floats represents the projection of the vector on the ith dimension. So here we see examples of some vectors in 2D and 3D. But why do we care about these vectors? Because machine learning models can be trained to represent real-world information like documents and queries into these n-dimensional vectors, such that documents that have a higher real-world similarity to the query have their vectors closer to the query vector. Now, how do we determine this closeness? So we have a few vector similarity measures. One of them is like Euclidean distance, which is just the direct distance between 2 points, or something like a cosine similarity, which takes the angle between two vectors into account but not their magnitude. We also have something called dot product similarity, which is just like cosine similarity, but it also takes the magnitude of vectors into account. So now that we can establish similarity between two vectors, so our problem now boils down to finding the k nearest neighbors for an incoming query vector with the hopes of finding the most relevant results for that query. But as you can imagine, like finding the similarity scores between the query and each of these document vectors can become super expensive, which is why there exist some algorithms known as approximate nearest neighbor algorithms, which allow us to find these k nearest neighbors like with some approximation. So Faiss is a feature-rich vector search library, and it has lots of algorithms related to this approximate nearest neighbor search. So the first class of algorithms, this first class of techniques is called vector encodings, where you basically store the raw vectors with some loss in information. And the goal of doing this is to speed up individual similarity computations and or reduce the storage costs for storing them. So one example here is scalar quantization. So a vector is just a series of floats, and each float takes up 32 bits and can represent values from -infinity to +infinity. But what if most of your vectors lie within a smaller range, say like -2 to 5 here? So in this case, we can represent those floats using a lower number of bits by moving it like to another data type, let's say an unsigned integer that takes up 8 bits. So we just like shift the input range by a certain value and scale it up or down to map the input range to the desired output range. As we can imagine, some floats will lie in between two integers, in which case they are just approximated to the nearest value, and floats that lie outside this range are just clipped to the extremes. In increasing order of compression, like Lucene supports 8-bit quantization, which is like 8-bit unsigned integers in the range of 0 to 255, 7 bits, which is really just like 8 bits, but with the 8th bit always set to 0. So the 8-bit one was added very recently, and it's going to be released in Lucene 10.4, after which I believe the 7-bit one can be deprecated. We also have something called a 4-bit quantization, where each integer is in the range of 0 to 15, but you can pack two 4 bits into a single byte, so it uses half the space as the 8-bit one. And we also have something called a 1-bit quantization, which I thought was just like crazy. So all floats in like -infinity to +infinity are represented just using a 0 or 1. But it works surprisingly well for vectors of a very large dimension. And Faiss supports all of this plus 16-bit and 6-bit quantization. Another example of a vector encoding is product quantization, where instead of looking at individual dimensions, we break up the large vector into a number of fixed subvectors Now, along subvectors across all dimensions, across all documents, we perform a k-means clustering to come up with a fixed number of centroids. And we represent each subvector with its nearest centroid. So at the storage level, we just store the ID of the centroid, while the centroids themselves are stored in a separate file called a codebook. So the compression here is highly dependent on the dimension of the subvector that you choose, but PQ can give as high as like 90 to 95% compression. And to build the vector back, we simply look at the ID of the centroid and we look up the centroid from the codebook and we get an approximation of the original vector that we had. This algorithm is supported in Faiss but not in Lucene, and there's actually a PR asking for it, but I don't think it's being worked on actively. Faiss has some other algorithms as well. We won't go into detail in each one of them, but LSH attempts to group vectors into different buckets using a hashing function that puts vectors that are nearby each other into the same bucket. We also have something called a principal component analysis, which is dimensionality reduction, where we drop dimensions that have the least amount of information in them, and something called optimized product quantization, which transforms vectors in a way that such that when we finally perform a product quantization, the loss in information is minimal. And something similar for LSH. And the reason we can do these approximations is we don't really care about the precision as long as the relative ordering between the score of queries and documents is about the same, because we're just concerned with finding the k nearest neighbors for a query. Another class of algorithms is indexing and search algorithms, where apart from the raw vectors themselves, we store some additional data structures to speed up KNN search, but with some approximation. And the goal of these techniques are to cut down on the actual number of similarity computations we have to perform to find our vectors by outright not attempting to score against vectors that are farther away from the query. So one example here is inverted file indexes, or IVF family of algorithms, where we partition our whole document space into a fixed number of clusters, and each cluster is just represented by a single centroid. Now when a query vector comes in, we just compare it against all of these centroids and filter down on a smaller number of centroids, for which we'll then perform an exact search within all vectors that are represented by that centroid. So this allows us to outright not process clusters that are farther away from the query. This algorithm is supported in Faiss but not in Lucene, and again there was an issue asking for it, but I don't think it's being worked on. Another algorithm is a graph-based index called HNSW, or hierarchical navigable small word graphs. So this is the kind of standard algorithm that is implemented in both Faiss and Lucene, and it makes use of document-document similarities to create a graph-like structure. So HNSW is hierarchical, where it has multiple layers, and the upper layers have logarithmically decreasing number of nodes. And the hope is that in the topmost layers we have a very few number of nodes that are spread out across the whole space, so that we can make long range it allows us to perform long range jumps to reach the vicinity of the query vector faster. So the entry node is chosen at indexing time arbitrarily. So if we just add everything in a single layer, we need to perform a lot of short range traverses to reach the vicinity of the query. But HNSW allows us to have these upper layers with fewer number of nodes, so that we can jump through large parts of the graph and find a single best entry node for the actual search in the lowest layer. Faiss also has support for another graph-based algorithm called NSG. So NSG is short for navigating spreading out graphs, which is different, very similar to HNSW, but different in the sense that it has a single layer, but it algorithmically tries to create these long-range links, whereas creation of long-range links is probabilistic in HNSW. So in HNSW, the nodes that get assigned to upper levels are random, and HNSW hopes that they are spread out enough that we can make these long-range links to reach near the query faster. But it's possible to have an adversarial order of indexing, such that all the nodes in the upper levels are concentrated on a smaller part of the graph, such that we would the search on the lowest level would start at a point that is farther away from the query. So NSG tries to offset some of this cost to indexing time by ensuring these longer range links. So it's a bit more expensive on the indexing side, but it's a bit more protected from these adversarial cases, and This is supported in Faiss but not in Lucene. Faiss also supports something called a composite index or refined search, where you can mix and match any of these different techniques I mentioned above, and it also allows you to do a first pass using one kind of index and then re-rank the results using another kind of index. There is some support for this in Lucene as well recently, where Lucene allows you to do a first pass using a scalar quantized vectors and then re-rank them using full precision vectors. But I believe it's a bit more generic in Faiss. So with all of these different kind of algorithms, how do you even pick which one to use? So Faiss has this nice guideline on which kind of index would be more suitable for your data, depending on how many vectors you have, how frequently you want to search them, the search versus accuracy trade-offs that you have, and the amount of memory you're willing to spend for it. So we won't get into the graph right now, but yeah, it's a cool thing to look at. Faiss supports all of these features on all major platforms like x86, ARC64, Windows, and even OS X. So this is also true for Lucene. Faiss also has support for SIMD instructions. So these individual vector similarity computations have a lot of repetitive instructions in them, and modern CPUs have optimized instructions that can perform a lot of these in parallel, called single instruction multiple data. So I think Mike talked about it in his talk yesterday, so I'll skip over this. But yeah, these are the instruction sets supported by Faiss. Lucene supports all of these to a large extent using its incubating vector API, where it allows you to represent these parallelizable instructions as Java objects, but you're still limited by the JVM's vocabulary of the instructions that it has. So it's known to there's a known issue in Lucene where the JVM isn't able to perform compile to the most optimized instruction for some machines, especially AWS Graviton instances. And yeah, the exciting feature in Faiss is it also supports GPUs. So it has GPU equivalents for all of the indexes and techniques I mentioned above, using NVIDIA's CUDA platform or AMD's RSCM platform. So fun fact, there was another PR in Lucene which attempted to perform a GPU-based vector search using NVIDIA's CUVS library, but this library is already implemented in Faiss, so we may have a shorter way of getting there using this Faiss integration. It's not there yet, we'll get to it later. So with this, the motivation to integrate Faiss into Lucene is pretty clear. It's a dedicated vector search library that has lots of things to speed up KNN searches and for very specific use cases as well. So we want to provide a low overhead way of testing all of these Faiss algorithms in Lucene before having to re-implement them in Java. I want to mention that in the long term, we definitely want to have everything within Lucene because it just gives us a higher level of control over all of the algorithms. But this just acts as a sort of short path to test them out before making that investment. So how do we do this integration? So Lucene makes it super easy with its Codec APIs. So Codec is just a collection of formats. So you can keep using your existing formats for doc values postings, but you can now plug in the Faiss KNN vectors format instead of Lucene's native HNSW format. And not just that, you can do it on a per field basis as well. So in your index, you could have some fields that use Lucene's native HNSW and some fields that have this Faiss-based vector search format. And internally, all this format requires you to define is a segment level writer that supports per field indexing and merge, and a segment level reader that supports per field iteration of float vectors and a per field KNN optimized KNN search function, and the maximum number of dimensions supported by the format. So here's the actual PR where we made the integration. So it's going to come out in Lucene 11. So the high level design which we wanted with this PR was it should be minimally invasive. So no external dependencies to Lucene core, and especially not native code. That was made pretty clear. We also did not want any API changes. We used whatever was already exposed by Lucene via its KNN vectors format. And this is a sandbox only experimental format, so there's no guarantee of backwards compatibility right now, because the internals may change over time. So on the high level, the Faiss format just has two files. One is a data file where we store the per field Faiss indexes just one after the other in contiguous blocks on disk. And another is the meta file, which actually allows us to map the fields for which those Faiss indexes correspond to. This is very similar to how Lucene stores its flat vectors today. So here are the steps that go into building a Faiss index. So we'll go into them in a bit more detail. So to create an index, Faiss has something called an index factory. I like to think of it as a sort of magic string. So it just allows you to describe any arbitrary index in Faiss using very simple grammar. For example, if you wanted a Faiss index that searches through all vectors in a brute force way, you could just say flat. If you want to perform if you're willing to get more approximate results for a fastest latency, you could move to graph-based indexes. So you could just say HNSW. At this point, you can start setting indexing time parameters. So 32 here represents the maximum number of connections for each node. At some point, if you feel the raw vectors are taking too much space, so you can tell Faiss to just start quantizing them into 8-bit unsigned integers by adding the small suffix. And before this, you can even ask Faiss to perform some dimensionality reduction to bring down the number of dimensions from whatever it had down to say 64. And all of this just means changing the input string to the index factory, and Faiss takes care of everything else internally. And we have NST equivalents for all of them. Similarly for the IVF family of algorithms. So 5 into here is the number of centroids we have. So one cool thing I thought was in IVF, if the number of centroids are too large, Faiss also allows you to filter down on a smaller number of centroids to look at by searching through those centroids using HNSW. Not just a pure search for all this, for comparing against all of the centroids individually. And Faiss also allows you to perform arbitrary defined arbitrary composite indexes and perform a first pass using one index. For example, HNSW with 4-bit scalar quantization, but then define the results using full floats. And it allows you to get as arbitrarily complex as you want. So once we have an index, we need to set some indexing and default search parameters for it. And Faiss also allows you to do this using a very simple string called the parameter space. So here EF construction corresponds to the beam width parameter that we have in HNSW. So you just have to specify key value pairs, comma separated, and they'll just be set on the index. And some of these may also be search time. So this is just the default search time parameters that will be used by Faiss. Once we have an index, we need to train it. So training just means passing a representative subset of vectors to Faiss so that it can train some internal data structures. So not all indexes require training. For example, HNSW by itself is good to go. We can just add vectors and add them into a graph. But for some techniques that require the distribution of the vectors to be known beforehand, for example, scalar quantization or product quantization, so it actually needs information about how your floats will look like before it can actually start indexing stuff. So once the index is trained, we can start adding document vectors to it. So this is as simple as copying document ID and vector pairs from Lucene to Faiss and then making an indexing call in Faiss. Once we have an index ready, we need to serialize it. So Faiss had reader-writer classes for file I/O, you could directly read and write from a file. But Lucene in itself Lucene makes no assumptions about where you have your index. So it has the generic index input and index output classes for I/O, where underlying you could have it on disk, on memory, even on heap if you wanted. So in order to support these generic index inputs and outputs, they actually needed to make changes to upstream Faiss to support this custom I/O, where it basically just lets Faiss call functions in Java so that it can pass bytes around. Once you have your index, once you have the Faiss index inside your Lucene index, at the reader side you need to read it back, and you can then start searching it. So searching simply means copying the query vector down to native memory for Faiss to access it. Then you make a call to Faiss to search its existing index using the query vector you just passed, and you then copy the document IDs and scores back to Lucene. So this seems easy in general, but Lucene's segmented architecture made it a bit tricky. So Lucene has this write once, read many times segmented architecture, where once a segment is written to disk, it cannot be modified. But what if you get updates for a document in an existing segment? So that document just gets marked as deleted in the existing segment and ends up in a new segment. So this means that while you are searching a segment, some of the vectors may no longer be live for that segment. So the way this liveness is checked is using a bits interface, which is essentially just a mapping of document IDs to a boolean whether it is like live or not. So in most cases, this bits interface is implemented by a bit set, which is just a series of like boolean bits. So where the ith bit represents whether the ith document is live or not. So in Java, this is backed by a array of longs. So each long is just like 64 bits, one after the other, where the least significant bit is like on the right and the most significant one is on the left. So Faiss does support filtering by bitmap. A bitmap is essentially a bit set, but it just differs in the way it is actually bagged on disk or like in memory. So Faiss, like these bitmaps are ordered like backed by arrays of unsigned 8-bit integers. So you can see there's some subtle differences in the actual way the bits are stored like between Java and within Faiss, where like the first byte here is like the rightmost byte inside a long. So it turns out you can just serialize a long using little endian byte order, and you can get equivalent representations, the equivalent bitmap within Faiss. So we did need some changes to upstream Faiss in order to like expose it correctly and like pass it down to all like searchable indexes. But yeah, we got those in. So at the communication layer, we make use of like Java's new like project Panama. So it's meant to interconnect the JVM and native code. And the features we are most interested in are foreign function interface, which basically lets us call functions inside Faiss from Java, and native memory management. So allocating, deallocating stuff in native memory, copying data between the Java heap and this native memory, and providing a thread-safe access to that memory. So Panama is pure Java, and it's considered safer and more efficient than earlier alternatives like KNN. So a benefit of Panama is it has no glue code. So you do not need C functions to actually make those calls to Faiss, allocate memory allocate stuff in native memory and copy things from the Java heap and back. But the con is like there is no glue code, so we have to rely like whatever APIs are exposed by Faiss publicly, and even if you want to write a thin wrapper on top of any Faiss functionality, you actually have to go back to Faiss, add it in, and wait until it's actually released. So in this regard, like the Faiss community is super active, and they had been like really helpful in accepting the changes that we wanted to make this codec possible. And some alternatives here are like the Java native interface, so JNI, which was the predecessor to Panama, where you need like glue C code to like do all the stuff I mentioned. So one important shout out I wanted to give was OpenSearch's Faiss KNN plugin. So it's very similar to what we're trying to do in native Lucene, but it's specific to OpenSearch, and it uses JNI to write a Faiss-based KNN vector search format. So how do we use it? So Faiss is vended by something called Conda, which is just a package manager. So installing it is as simple as running like conda install Faiss CPU. But you should be beware of the license for Conda. So Conda itself is open source and free to use, but by default it is configured to use a channel that is proprietary. So luckily for us, most of like all of Faiss's dependencies are present in 2 channels that are free to use. But if you don't want to get into all of this licensing, it's open source and you can just build it from source. At runtime, once you have those shared libraries and dependencies, you just need it to add it to your Java runtime, either as a JVM argument or as an environment variable. So yeah, let's get into some benchmarks. So okay, so this is a recall versus latency trade-off. So all of these different, so in this setup, so we used cohere vectors, which are one of the like standard ones used in upstream Lucene benchmarks. We have 768 dimensions. They are full float vectors. So I use the dot product similarity measure, and we are indexing everything in a like pure HNSW index. So the different points you see here correspond to different indexing time parameters. So I should note here that Faiss, by default, the inputs given for those indexing parameters were same for Faiss and Lucene, but Faiss somehow produces values that have a higher recall but for a higher latency. So internally, there are some subtle differences in the way HNSW is implemented in Faiss and Lucene, But for an end user, what they really care about is this recall versus latency trade-off. And well, from this line, it seems they are about the same. So that's like that was nice to see. But yeah, when this PI was first merged, so Faiss was actually consistently faster than Lucene by about like 15 to 20%. But over the like past couple of months, there have been improvements in Lucene for bulk scoring of like float vector values, which like brought this difference down, and now it's about the same. And here's the corresponding indexing time performance. So Faiss is a bit slower, but as we just discussed, like you can get away with using like lower indexing time parameters because it does for the same params you get a higher recall order. So some high-level drawbacks of like adding Faiss into Lucene is it's an external library. So as a user like inherit all Faiss bugs implicitly. So even if you like want it or not. And the sad part here is since it is written in C++, like most of those errors are non-recoverable. Like you may run into segmentation faults. And even for checked exceptions in Faiss, it's a bit tricky to get to try to read through them in Lucene because Faiss just has like a global variable that says like this is the last known exception I saw. But if we run it in a multi-threaded environment, like that may keep getting updated all the time. And turns out it's actually not safe to like read that. And since Faiss is in like native space, there'll always be a communication overhead of like copying stuff to and from the Java and the C layer. And of course the developer overhead of like having to deal with two different libraries, some of which like they aren't really familiar with. Some other caveats of like our integration in specific is we need a copy of raw vectors in Lucene. So some indexes in Faiss like drop information about these raw vectors. So say for example, if you enable scalar quantization, the original floats are no longer kept around in Faiss. So but during merging of segments, like you actually need the original vectors themselves. So Faiss allows you to reconstruct vectors from whatever it has, but this is lossy. So you do lose some information in trying to build the vector back, and as you have more and more successive merges, this loss can compound over time. So to work around this, we store a copy of the original vectors in Lucene that are not used at all at search time, but just during writing. And in fact, Lucene does something similar in its own like internal scalar quantized vectors. Like it stores a raw copy that is used just during writing and not during searching. Another caveat is parallelism. So Lucene supports this multi-threaded HNSW graph construction that again Mike talked about yesterday. So, but turns out search operations in Faiss are thread safe because they don't change anything, but indexing isn't. This just means that you cannot call Faiss from like multiple threads inside Java. This does not mean that you lose any multi-threading support overall. So Faiss does have something. Faiss does support internal multi-threaded graph constructions using an environment variable called like OMP num threads. So it just means you cannot use an executor in Java to perform like a multi-threaded graph construction. You just have to set this environment variable. And another thing is query level configuration. So Lucene just has HNSW today, so the only query level config it passes like the K I want. But different Faiss indexes have a lot more search time parameters, say n probe in IVF, that Lucene doesn't currently have a good top level APIs to pass down to Faiss. So yeah, there's lots of future work with this whole Faiss-based vector format. So from the maintainability perspective, like we would like to expose this configuration via safe schema. So right now it's sort of this free-for-all string that makes it very easy for the user to like shoot themselves in the foot. Like let's say they make a simple syntax error, or let's say they pick an encoding that's not really suited for the index type they are using. So it allows the user to be super flexible in what they want from Faiss, but it also makes it that much easier for them to like pick a wrong configuration. So we would ideally like to map all of these features inside Java and expose it as a like safe configuration and build the Faiss index internally inside Lucene. And yeah, another thing is like since it is in native code, so how do we identify longer running issues like say memory leaks? On the functional side, so Lucene has timeout support within KNN searches, where since everything is in Java, so while traversing the HNSW graph, it can check whether like a timeout has occurred or not and just stops us immediately. But in Faiss, you make a native call and you like hope it completes within your time. So today, the integration doesn't have good support for timeout within Faiss, and this is something we'd like to add very soon. Byte vector. So Faiss just supports indexing float vectors, whereas Lucene also supports directly indexing byte vectors that were say quantized outside of Lucene by the user. So the user just specifies byte vectors which are signed 8-bit integers, and Lucene can index them using any arbitrary vector similarity computation, but Faiss does not allow that today. I think OpenSearch solves this by upcasting the byte vectors to float vectors and then using Faiss's scalar quantization internally. Another thing is a parent join query. So in Lucene we can have child documents where each child document may have multiple vectors, and we'd like to perform a KNN search which diversifies the unique parents that we saw. So since everything is in Java, so this can be done in Lucene, but this information cannot be passed very easily down to Faiss, and this feature is not supported today. On the performance side, so Faiss is super memory hungry, so it just keep loads everything into RAM greedily, not just the graph indexes but the raw vectors themselves. So there has been recent improvements to Faiss to add memory mapping support, but our integration does not make full use of it today, and we'd like to do that soon. Faiss, while in itself supports SIMD instructions, the default by default the library links to a version that is non-SIMD optimized. So at runtime, Faiss also vents different versions of the library for different versions of SIMD, but we need some more plumbing in Lucene to figure out which is the most optimized one available at runtime and link to the correct one. So that is not done today. While Faiss has support for GPUs, so we do not use them from Lucene today. So a big reason is we get queries one after the other, and there is no query batching present in Lucene today. And GPUs are mainly beneficial when you can run a large batch of queries today. So we couldn't implement this directly because this whole batching layer was missing. But this is something we would like to take up soon. Improving merge time. So when merging SNS2 graphs across multiple segments, Lucene is able to reuse information from an existing graph and just add vectors from the other graph into it, as long as there are no deletes. But this kind of thing is not possible in Faiss because it doesn't have these bulk merge APIs where documents can be dropped in the middle, some things can be reordered and so on. So for Faiss, we need to create a fresh index for every merge, whereas Lucene has this benefit of reusing some information, from previous segments, and some more things around improving the memory of our integration. So yeah, that's pretty much it.
I'm curious a little bit about how it is to work with the Faiss community. You said they were super responsive and stuff, but what's their governance model? It's
they weren't super responsive, had to get behind them for a lot of changes, but they were willing to take changes. It's just that the timelines were a bit bad. But yeah, I think all the committers in Faiss today are based in Meta. It isn't super broad where someone outside Meta could merge it in. So that's a bit of a challenge.
How frequent are the releases?
About 3-4 months or so.
Hi. Well, thanks. One, it was interesting to see how competitive really Faiss was with HNSW and showing how far HNSW in Lucene has come along. So I don't know if you were expecting that, but having seen that now, I'm not sure would I use the Faiss codec given
So this comparison just showed whatever algorithms are present in Faiss and Lucene today, and the common one was HNSW, but there are a lot of different indexes and indexes that may be more suitable for specific types PQ or an IBA family of algorithms. So that isn't there in Lucene today. So the main benefit of the Faiss codec is the ability to use these different types of indexes.
IBF would be much faster to index, for example. So you might prefer it for that reason.
So I still don't know much about vector search. I'm still learning about it. So I think there were a few things I was able to learn through the presentation. One thing that really caught my eye was being able to support different formats for different fields,
Yeah.
right? So we are able to do that for KNN format, like that's really cool. I was just wondering, like, is that something we can do for like other codec, other structures as well, like doc values, point values, and all? So
For KNN, like each field, so each field has their own separate HNSW graphs. But let's say something like terms, it may be more beneficial to like have a common terms dictionary across different fields in order to reduce stuff.
I
So
think-
the benefit is the individual fields have their own separate data set, and by default, like we can't really do much even if we had information about vectors from another field. Like we would still index them separately, which is why it works really well with a per field format. But yeah, I don't know how other.
I think even for term dictionary and all, it is indexed separately.
Yeah.
Yes.
You
It's
Yeah.
just like kind of stored together in a single file. So
No.
I
Lucene is very per field. The only thing not per field I can think of would be stored values. Maybe there's something else. So it's
Yeah.
very separated.
Yeah.
For a long
Yeah.
time, you can have different. I've used many different postings formats, different doc values formats, and it's separated. And
Yeah.
there's a separate format fitting underneath the codec that separates them all. That is the norm. That is how things are today.
yeah, so I'm wondering, like, is it say possible to like I have a document, so I want to put some fields in one format and
Sure.
some fields say like in a Parikh, like I want to plug in Parikh as a format into that. So I think probably one of the big challenge will be like having some sort of reader on top of that, which can like produce doc values or points format.
It's a lot of work to write these codecs. I've written some. Yeah, they're separated though. You can do what you want in different ones. I've seen encrypting ones. I've seen, custom ones we wrote.
But can you customize the storage layer per field? If you want to put some of your fields in one directory and some of your, I don't know.
No. No.
So,
Go ahead.
okay. Thank you. So, I mean, the indexes, they are essentially Faiss native, right?
Yeah.
And how, I mean, is there a concept of merges and stuff like that for those indexes?
So
And do we have
Faiss-
any control over that?
Faiss doesn't like support natively merging stuff and at the same time like dropping documents in between as it may happen in Lucene. So in Lucene, when merging two segments, like some documents will be marked deleted. So when those are merged, like the documents are dropped and they no longer have to be put into the same one. Faiss doesn't have these like such highly specific merges, like merging of two indexes, while also simultaneously dropping stuff like documents may be compressed, and so for this reason we need to we today make these Faiss indexes from scratch. So Faiss in itself doesn't have merging entirely. All of this is called like on a per segment per field basis from Lucene.
Sure, but I mean, firstly, the question maybe should go down to whether Faiss even has a concept of segments and what happens to deleted nodes. I mean, the deletion is handled at Lucene level through doc ID, like marking it in the bit set sure. How does that reflect in the HNSW graph in Faiss? Like, how does it keep track of what nodes are no longer a part of this graph, or is it handled at the
During
Lucene level?
search time, are you mentioning about search time?
So I'm talking about say deletions. If a node is deleted, right, is in the HNSW graph in the native Faiss format, does Faiss do some
So-
kind of optimization to remove them from the graph? Is there a
No, so
way?
if
or-
it is deleted, so Faiss doesn't we don't really delete it. We just pass it as a search time filter that this document is no longer live. So
Oh,
that
okay.
happens at search time. At merge time, Faiss doesn't have any information about the previous index that it saw from original merges. It just builds everything from scratch.
Okay, so essentially the graph just keeps on growing.
No.
So there's no
It's a new graph for every segment.
There's separate graph for every.
Okay.
And when multiple segments are merged, a new graph is created
Okay.
for the new segment.
Okay. Got it.
And it's useful to know, we keep saying Faiss doesn't support merging, but what really is, Faiss takes the approach of a mutable index. That means you can add, you can delete. When you're strictly talking about Faiss, you can add, delete, do everything. Just like B trees, right? They can be updated in place. Whereas now, since we want to bridge Lucene to Faiss, then we need to map Lucene's concepts of segments into each individual Faiss indices, and we soft cache the deletes, and we translate merges as building a fresh Faiss index. So that's the responsibility that I think Kaival talked about. And search time, we address the correctness with the filter.
So you're saying we could, in theory, actually delete the nodes from the Faiss graph if we wanted.
Right.
Yeah.
But then like in Faiss we index them as like document vector pairs. So if we delete something and it goes into a new segment, the documents are reordered as well. So it's a bit Faiss doesn't provide as many APIs to like reorder stuff, and so we
I was curious, the OpenSearch integration. OpenSearch integrated Faiss before your change to Lucene, and a long time ago, and did not use the Codec API. There was some different sort of level of integration.
Codec API, they have a KNN based, like KNN vectors format as well. It's based on JNI, but I think it cannot be used independently from Lucene, like from other users of Lucene. Like it's tied to open source.
Because it's using like OpenSearch logging APIs or something. Because it's such a low-level thing. Okay. Well, that was the second question. That was a quick answer, so I want another question. Is that graph you made that showed the nice recall that Faiss got beyond Lucene and latency, like it could go up further, the curve could go up further?
Yeah, so
were you changing the same parameter, like EF such and such? Was it the same parameter, same values to both Lucene and Faiss?
Same parameters provided to Faiss and Lucene.
Same graph connectivity? Like, did Faiss give a bushier graph? Like, what was the source of the difference?
There are some certain differences in the way HNSW graphs are built in Faiss and Lucene. Like Lucene has this diversity check, and there's some other like differences in the way graphs are built. So while we gave them the same indexing parameters, Faiss just like produced a higher recall at the cost of higher latency.
And was it a bigger graph? Did it take more edges or something?
It's about the same. Like the worst case is capped by max connection.
Yeah. Okay. Worst case is capped, but maybe Faiss used more. Lucene doesn't always use exactly max connections, right? So maybe it was bushier in Faiss. Yeah.
It does something's fishy, right?
Yeah.
What's
I
going
don't
on?
like that. I feel like Faiss somehow got more magic out of each arc or something.
No, but at the
Well,
end,
it's
the
slower.
recall versus latency data
I know.
was about the
brute
same.
force and
Yeah.
fail it.
No, I don't think the slowness is something to bash here, because we don't know if even if we construct the Lucene this is to achieve 0.95 recall,
Yeah.
the latency would probably be like same, at least ballpark.
Yeah,
if
yeah,
not
It would be about the same.
I'm
it's
more
just for
concerned about why we
latency
can't drive Lucene up to there as well
Right.
with the
Well,
same
maybe we
parameters.
can.
Maybe you can. I just wanted to.
I know, but
demonstrate
with the
that
matched parameters, I thought with the matched parameters, HNSW is kind of a well-defined algorithm. Two different implementations of the same algorithm with same
I will
inputs.
say the diversity criterion is a well of confusion, so that
Okay.
could be part of it. I
But
don't
is
know
it
what
possible
else.
Lucene has bugs in its diversity thing, and that's why we're not getting up there? So I'm nervous about the fact that those dots don't agree.
I think we might be eliminating too many things. We're too, yeah. Anyway.
Okay.
In this for latency for the Faiss codec, was this with the SMIT instructions and
So,
for
yeah.
GPU? Is it using
Yeah,
the
everything is pure CPU. We don't support GPUs today in Faiss. This is the CPU.
I have a very subtle question. So how do we bridge the doc IDs across Faiss and Lucene?
So Faiss does support indexing stuff along with doc IDs. So we just like compute the doc IDs in Lucene and just pass them over to Faiss.
So we treat it as a payload as the
Yeah.
Faiss. Thanks.
You said that you were linking against a version of Faiss that did not support SIMD
Yeah,
instructions. Do you
Yeah,
think
that's
that
the-
would change this graph?
Yeah, it would probably speed up like Faiss's whole thing by like a certain factor here. Like this is the non-SIMD version of Faiss. So if
Right.
we link to the SIMD version,
But
And
we are
Lucene-
using SIMD and
Lucene does
Lucene here.
use-
In theory, Lucene is using SIMD.
Oh, totally unfair.
Oh boy. The situation got even worse than I was thinking.
Okay, we're at time. Thank you so much.
Thank you.
very much.